All right. Do we have any questions from yesterday? We covered quite a bit. We talked about variables, we talked about memory, we talked about sort of a mental model of how we think about variables in terms of memory and how memory impacts our understanding of variables. If you've never seen C or C++ before, a lot of that might be new to you. Today is going to be a much shorter, much easier lecture. If you've done any programming at all, a lot of it will look familiar. Today we're going to focus on control structures in C and C++. These all appear in C++ as well. These include conditionals, loops, and jumps. We've seen conditionals already. We saw if yesterday. We saw a for loop yesterday, I think. I don't think we saw any explicit jumps yesterday, but we saw some implicit ones, and I'll talk about the difference. So yes, okay, yesterday we did variables, life cycles, scope, types, representation, and memory. Then we talked specifically about memory, the different types, how we manage it, our responsibility as programmers for doing so. Today we'll talk about conditionals, and there's really only 3 cases for each of these different types of structures: conditionals, if-else, switch case, and what's called the ternary operator, if you haven't seen it before, or ternary expression. Loops, for while and do while, and then jumps, break, continue, and go to. Let's start with conditionals. Conditionals are control structures whose evaluation modifies the path of execution in a program. This is kind of abstract. It's really referring to your mental model of how things progress through a program. In C, there are several instructions for conditional statements. This includes if-else, switch case, and the ternary expression. We're going to look at each of these in turn and how and why you would use them. Before we do any of that, you might expect that we need to review logical expressions, because these are necessary for us to use conditionals. So logical operators in C are binary operators which test the truthfulness of some bit. For 2 booleans, 2 1-bit values, it's pretty easy to enumerate what these expressions yield for all possible inputs and all typical expressions. So in this table we have A, and then an operator, B, and the evaluation of A with that operator with B. So if A is 1 and B is 1, then the evaluation is 1. If one of those is 0, then it's 0. If they're both 0, they're 0. That's how the AND operator works. This pipe, the vertical line, is the OR. So 1 or 1 is 1, 1 or 0 is 1, 0 or 1 is 1, and 0 or 0 is 0. This should probably not be surprising, though you maybe haven't looked at it in terms of 0 and 1s. You've probably looked at it in terms of true and false, depending on what language you're most comfortable with. In this short demo program, we're using standard bool so that we can actually have booleans. And we just have A equal 1, B equals 0, and then we test various expressions. These are logical conditions, so we're testing if A is less than B, A is greater than or equal to B, A is equal to B, A is not equal to B, A is greater than or equal to B, and A is less than or equal to B, and A or B or not greater than or equal. There's no print statement in this program, so if you compile and run it, it will do nothing, of course. But if you included a print statement for each of these, you'd be able to enumerate a table like this for more complicated Boolean expressions given these 2 inputs. And that can be quite useful if you're trying to work through the logic of your program in some simplified state. I've certainly done this in the past. Now, the basic conditional logic structure is an if statement. You're probably familiar with if statements. This defines a code block which only evaluates when the condition is true, and you can optionally provide an else block which evaluates if the condition is not true. So let's say you want to evaluate the sync function, which is sine of x over x, for some input double x. We, of course, need to take care when x is equal to 0, because 0.0 over 0.0 is c, shorthand for not a number. That is, if you divide 0 by 0 in c, the world doesn't explode, it just tells you it's not a number. This can be really annoying if you're writing numerical programs, because that not a number will then propagate to everything that this touches, and you'll just get a bunch of nans out and you don't know what's happening. So, in order to evaluate the sync function, we need to capture a particular case based on the input value and yield a different result in that case only. So this is a pretty good use case for an if statement. Here, we're going to write our sync function in terms of if and else. It's inside of a main function because that one's necessary, but you could write this in terms of a header library if you preferred. So we have double x, and we're setting it equal to 0.1, and we have a double sync, which is not initialized. If x is exactly equal to 0, then sync is equal to 1, else sync is equal to sine of x over x. Now you might expect, based on what we said yesterday, that there's a subtle issue in this program. Can anybody put in the chat what it is? It's in this condition here. We're checking if a floating point value is exactly equal to 0.0, which typically it never will be. But in fact, this is not sufficient, because there are two zeros in floating point numbers. There's a plus 0 and a negative 0. So what you'd actually want to do is check if the absolute value of x is less than some very small number. That'll include 0 and some range that you can tune based on the numerical accuracy that you need in order to yield 1.0 exactly where you need it to. This is a subtle thing. It's something you would probably discover 1,000 lines later in your program when your sync function is not giving you the correct result and you don't know why. But it's good to keep an eye out for this sort of issue. Additionally, there are some syntactic pitfalls with these conditional statements. So in this program, we have a set equal to 0, b uninitialized. If a equals 0, b equals 1. If a is not equal to 0, b is equal to 1.0 divided by a. Can anybody spot the issue in this program? So again, it's in this conditional statement. Here we've used one equal sign, which is an assignment of 0.0 to a, rather than checking the value of a to be 0.0. So this is a pitfall in these conditional statements because you need to use two equal signs to check for equality. This is something that appears in programs. It's just a typo. But it can lead to unexpected results because not only are you not evaluating the condition that you thought you were, but you're actually changing the value of one of your variables, presumably an important one, because you have it in a conditional. So a way to fix this is to just use two equal signs. There's another pitfall here. This one I think is more obvious. On the left, we've used curly braces to denote a specific scope for these if conditional statements. And on the right, we have omitted them. So we're relying on an implicit scope being recognized when the program is compiled, so that b is set equal to 1 if and only if a is exactly equal to 0.0, and b is equal to 1.0 divided by a if a is not 0. However, this is typically considered bad practice because these curly braces on the left here mean that this whole thing is a complete expression, whereas here you are relying on this implicit line following the if in order for that to be evaluated correctly. In a simple program like this, it's easier to spot, especially if you helpfully include unusual white spacing to help the reader. But in a larger program, it's very easy to overlook this sort of thing. So I think the resolution for the second case is to just use curly braces all the time. Now, we've seen if. I've left off else because it's just not very interesting. You certainly thought about it before. Enumerating multiple nested if-else statements is a tedium even C could not abide. There's a lot of tedium in C, but apparently having nested if-else statements was a step too far. In this scenario, we have what's called a switch case, where we specifically enumerate the possible values an expression can evaluate to, and define independent code blocks for each option. Case testing in a switch statement is exhaustive by default. This is different from a lot of other programming languages. So if we had many cases, then checking for a match exhaustively becomes more of a cost. You can avoid this by adding break statements to the end of each case, so only the first match is evaluated. This is something that comes up as a bug in a lot of programs. In fact, we'll see if I remember to fix it in the slides shortly. So by providing a default case for these switch cases, you can also specify matchless code, which can be quite useful. Sort of, you give it a default value, for example. In this short program, we set int day equals 1, and then we switch on the value of day. Case 5, weekend tomorrow. Case 6, still weekend tomorrow. By default, back to work tomorrow. In this snippet, we match on the day of the week, and we lament the return to work by default, but provide special cases for Friday and Saturday. I'm assuming that, the week begins on Monday. You'll note here that there's no break statements in these cases. So if you wanted it to match exclusively on 5 and 6 and not proceed to the default, you would put in a break statement here. Now, conditionals, the if-else statements, are very widely used in C. Switch case, less so. Switch case is something you kind of do a lot for programs users have to interact with, which, frankly, I don't think you should be using C for. One thing you'll also see quite a bit in numerical codes or scientific computing codes is this ternary operator. This one's quite weird. You may not have seen anything like it before. It's a compact way to represent the logic of an if-else statement, but as an expression, so it's more expressive. Using it is quite easy. So in this short program, we have double A set equal to 1, and then we have B and C, which are uninitialized. B is assigned to 1 over A if A is non-zero, otherwise it gets a 1. So what you do is on the right-hand side of that assignment, you have an expression which evaluates to a Boolean, followed by a question mark, and then the true option, and then a colon, and then the false option, and then a semicolon. This is not especially legible, I think, if you're not used to seeing it. So I would recommend you avoid using this in programs in large programs. In short programs like this, it's probably fine because you can afford to reason about these assignment statements for B and C, but generally in large programs, it's much harder to follow. Also, in a lot of modern languages, the if-else statement itself is an expression, so you can just use it on the right-hand side. The utility of this is because the ternary operator is an expression, you can use it in an assignment on the right-hand side, whereas in C, you can't use the if-else statement there. So this program, B just checks the value of A and then gets one of two values. C checks the value of B and gets one of two values. And then D is an int, which is assigned either to the output of printf or to 0 based on the value of C. This is valid. Printf does give you an output value. It's just an integer denoting standard return. But again, if you haven't seen it before, this can be quite confusing to follow, especially in a large program. Conditionals are nice. We need them for loops. Loops are way better. Loops are the backbone of scientific computing. And largely, hand-wavy overall. The story of ergonomic high-performance computing is a statement about adorning loops with information so the compiler can do some extra work for you. When you take high-performance computing with me in November, you'll see quite a bit about loops and how we can add information to them in order for them to be done in parallel. So this loop section will cover the basics of using for while and do while loops, and we'll discuss a little bit about what you'd use them for typically. Starting with the for loop, because this is by far the most common, the most useful. For loops require explicit use of a counter. So you're giving it a range over which it should iterate. You have to give it a termination condition. So when that evaluates to true, the for loop continues. And you have to give it an increment. Typically, this is just +1, or you might multiply by 2, or do something more interesting. But in general, it's just an iteration range. In the simplest case, we know how many elements we want to iterate over, and we proceed from the least iterate to the greatest. And because we know the range of the loop beforehand, this is ideal for for. This is also why for loops form the foundation of thread parallelism or high-performance computing with shared memory, because you typically know how much work you have to do beforehand. In this example program, we have n equal to 10, and we create an integer array of n elements called a. And then we have a for loop starting at index 0, int I equals 0, I less than n, I plus plus, and then within the body of that loop, we just set the ith element of a to the value I. Simple enough. So here we're just filling that array A with 0 through 9. 0 through 9 inclusive. This is maybe something you will struggle with if you are new to C programming. It's 0-based, so your loops typically start at 0, and that means that the size n here is going to be non-inclusive in your condition. If you did I less than or equal to n, you could segfault your program, because you'll be writing to memory that is not part of your variable a, and you might do something weird to your computer. Now, while loops don't have an explicit range, so they differ from for loops in that sense. They execute unless a condition is violated. The condition is checked at the beginning of each iteration. This is important to keep in mind. If you change how that condition is evaluated within the loop body, it won't get checked until the next iteration. This leads to some subtle bugs sometimes. If we wanted to fill the array from the for loop example using a while loop, then we have some options in terms of the condition checking. The most obvious is I less than n, since this is the same condition that we used for the for loop. In this simple program, we've just changed the for loop for a while loop, and because we're not creating a new variable I here, we need to create it up here and set it equal to 0 initially. But this does the same thing, and then of course we have to increment I inside the body of that while loop. Otherwise, I never changes, and you just assign A0 to 0 over and over and over again. That's something to keep in mind. The loop body is responsible for incrementing the counter I, otherwise it never progresses. You have an infinite loop in your program. If you've never seen this I++ before, this is just a shorthand for I plus equals 1, which is itself a shorthand for I equals to I plus 1. If you, say, wanted to make A an array of doubles, you'd need another line here where you say double A of n to initialize it. Okay, the third type of loop is kind of rarely used, but it's good to keep in mind because it does solve a problem that the for loop and while loop are ill-suited to solve. These are the do while loops. Like the while loop, they don't have an explicit range. They execute until a condition is violated. The condition is checked at the end of each iteration. So this solves a slightly different class of issues than the while loop. That way, they always execute the loop body at least once. So for example, if you're familiar with iterative algorithms, so for example, the Arnoldi method for approximating the eigenvalues of a matrix, you might want to use a do-while loop because it'll always evaluate that loop at least once to get your algorithm going, and you can always check for early termination in the body of your loop. In the following example, we want to iterate a map while the iteration is smaller than the initial value. If you evaluate this condition first, so if you're checking that the value is smaller than the initial value, initially that is false. So if you try to do that with a while loop, it would just fail. Nothing would happen. The do-while loop is a great way to solve this type of problem. So here we just have double r x0 and x equal to x0, int n equals 0, and then we have a do-while loop. So we have a do, and then we open the curly braces to denote our iteration, and then while, which follows the loop itself. While has the condition where it's evaluated. This is kind of helpful because it sort of visually reminds you that it's going to evaluate this loop at least once before it checks anything. This is just this map has a special name. If somebody knows it, put it in the chat. All it's doing is taking x to r times x times 1 minus x, and then incrementing n, the counter of the loop, and while x is less than x naught. In fact, you don't actually need this int n equals 0 or n plus plus here, because you're just relying on this condition to be evaluated. If you've never seen this map before, this is called the logistic map. It's responsible for a lot of fundamental analysis in chaos. This is like an archetypal model for understanding the period doubling route to chaos. Okay, so we did conditionals, if, else, switch case, and the ternary expression. We did loops, we did for, which is our bread and butter, our main one. We did while, which has its uses, and we have do while, which you rarely see but has its uses. Now we can talk about jumps. Jumps, in general, are statements that alter the linear, logical, legible flow of a program from the literal sequence of statements on the page, or on the screen in most cases, to allow code reuse and efficiency. Their use can sometimes dramatically increase the difficulty of following the execution of a program from the source code, but its limited use is sometimes extremely convenient. In this section, we'll discuss the use of break, its selective sister continue, and the weird cousin goto. I say weird cousin goto because I think you should avoid it in almost all cases. Now, the break keyword breaks out of a loop when encountered. That's all it does. This makes it easy to save work by exiting early. If it's easier to check the condition of the answer than it is to complete an unnecessary iteration. So say you have a really expensive for loop and you want to break early if it meets some condition because the iterations are quite expensive. You can use that as a way to break out. You can think of this as a hard counter to an infinite loop, but this does not give you license to use infinite loops. Infinite loops are still bad, even though break can get you out of them. In this program, we have a for loop from 0 to 99. We have an infinite loop, while 1, so this is just true, while true. If j is exactly equal to I plus 1, then we print something and we break out of the loop. And otherwise, we continue by incrementing j. If you run this program, this will increment until you reach j is exactly equal to I plus 1, and it'll print something out. So this is, in this case, sort of well-defined. You can kind of think about this and prove to yourself that this infinite loop does actually terminate. This is bad practice, though. This is a very contrived example. Typically, what you want to do is you have some expensive loop, and each iteration takes a really long time to evaluate, for example. But checking that you've gotten the answer you need is quite cheap. So you just have that check somewhere in your loop, and you exit early if you can. This only gets you out of the loop that you are in. So if we had two for loops, for example, break will only get you out of the innermost loop. In this case, it only gets us out of the infinite loop, this while loop. We'd still have iterations in that outer loop. As a counterpoint to break, there's continue, but instead of breaking us out of the loop, we break out of the current loop iteration. So we kind of skip what's currently being iterated and go to the next one. You can imagine a simple for loop with a condition I set equal to 3 at the beginning of the loop body. And if we put break in this condition, then everything after and including I equal 3 will skip. If we put continue in the condition, then only I equal 3 will skip. So that's what we do in this, well, we do a version of that in this example. We have two loops, I from 0 to 9, j from 0 to 9. If I is 5 and j is equal to I, so j has to be 5 as well, then we continue. We don't do the rest of that iteration. Otherwise, we're going to be printing I equal j equal. So it only skips I equals 5 and j equals 5. Everything else is going to get a print statement. So the continue statement is a simple way to skip a case here and there within a loop. In practice, I think this is quite rarely used. You're frequently not writing loops where you don't care about some of the iterations. Typically, you care about all of them. But it could be useful, say, if you had a really long-running while loop where you're solving some problem, and you want to print things out occasionally. You could have the main work being done in your while loop, and then a continue statement followed by a print statement, which is only done conditionally, for example. This is the real weird jump statement in C. You have maybe heard of GoTo before. GoTo is a construct for defining named blocks and directing the program execution to those blocks from anywhere in the program. The legitimate use case for GoTo is to escape from nested loops, because of course break will only escape the innermost loop that it's in, and it cannot pass the effective break to that higher scope, the outer loops. So in this example, we have our I loop from 0 to 99, j loop from 0 to 99. If I is equal to 50 and j is equal to I, then we go to the exit. And in the syntax, our exit is here, defined outside of those two loops at the end of our main function. And it just prints I equal j equal 50. If this does not evaluate to true, then we don't hit the GoTo. Otherwise, we hit the break, so we never reach this printf. And in fact, the iterations are skipped for j greater than or equal to 51, or 50. GoTo, as you can maybe tell here, makes a connection between this very late point in the program with this rather early point in the program. It can be very hard to follow programs with GoTo statements, especially multiple GoTo statements, especially GoTo statements that are evaluated conditionally. Please use GoTo responsibly, by which I mean never. I think in every case where you would want to use GoTo, there's a better way to architect your program to avoid using it. Keep in mind that the real difficulty of programming is not writing code. it's understanding code. When you use goto statements, you make it much harder to understand what's happening at the expense of making it a bit easier to write it. Now there's one more jump statement in C. It's a very important one that you'll use constantly, but we're not going to cover it today because you're going to see it quite soon. You may be able to guess what it is. It's the return statement. I've been leaving return out of my main functions thus far in the course. This is because we've had very simple examples and the compiler can reason about them so that it can show, return is needed or not needed. It can insert it itself. C is permissive in that sense, which kind of encourages bad behavior sometimes. But return is very important. Return escapes you from a scope, from a function scope typically. It's telling you that anything followed by return is a value returned by a function, and anything following that in the function scope is ignored. So today we've talked about conditionals, we've talked about loops, we've talked about jumps. Conditionals, widely used. Loops, widely used. Jumps, implicitly used, but not something you should really rely on, I think, in most cases. That's the end of the lecture today. If you have questions, please put them in the chat. Otherwise, we'll take a 5-minute break, and then I'll come back and talk to you informally about some of the eldritch horrors of C programming. Okay, let's talk about some of the practical aspects of C. We've covered quite a bit already. Covered memory and variables yesterday. We've covered control structures today. Once you learn functions in C, that's kind of what you need. And C is really considered like a very small, compact, simple language to get your head around. Except it's not. It's actually very subtle. Not in terms of the lexical content of the language, that's quite easy. We've seen a lot of it already. But the métier, the practical knowledge of using C, is actually very difficult. So this is a rather famous quiz called So You Think You Know C. It's been around for a while. Not as long as C, which has been around for 53 years at the time of writing this quiz. It's 5 questions about using C. I encourage you to think carefully about each question. The answers are sometimes not subtle, not obvious. In this first one, we have a struct S, which has an integer I and a character C to define the variable S. And then in main, we're just returning the size of a pointer size of dereference of location of S. Now, int I, this is some number of bytes. A character C is 1 byte. Int I is 4 or 8. Probably 8 on your machine. It might be 4 on a very old machine. So struct S is maybe 5 bytes, maybe 9. Let's go with 5. In the second one, character A equals 0, short int B equals 0, return whether the size of B is equal to the size of A plus B. Well, you're adding a character to a short int, but a character is like a really short int. If B is 0, then it's not going to overflow, it's not going to escalate. So the size of B initially is larger than the size of A, and we should be able to add those together. It might make sense that this is evaluated as true. It's certainly not 2. The Boolean statement should not give you 2. We have character A, which is the space character times 13, and then we return A. I don't recall what the space character is, but it's probably not negative. 416 seems like it might be a multiple of 13. I'm too lazy to check. Int main with void input, int I equals to 16, then we return I greater than equal to I, bit shifted by I. So this double chevron is a bit shift to the left or right. And then you bit shift by I again, and that's less than or equal to I. Again, this is a Boolean, so it's hopefully not going to return 16. I think this might be true. Int main void, int I equals 0, return I plus 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 I. I plus plus means I and then increment, plus plus I means increment I, then return. So I think that might be 1. Every answer I gave was 0, was incorrect. I got 0 points. The correct answer in all cases is I don't know. All of these are inconsistent in C. They have a very lengthy explanation of each of the questions. I encourage you to do the quiz yourself, even knowing what the answers are, and to read through the explanation, because it's kind of eye-opening about how this language, which has been de facto systems programming language for 50 years, is actually quite ill-defined in practice. Now, speaking of C as a programming language, this is a very fun read by Faultlore, who works, I think, primarily on Rust or programming languages generally. I'm not entirely sure. C isn't a programming language anymore. This is largely about how C became the lingua franca of all programming systems, and about how especially at the beginning, they explain a few things about how C is horribly ill-defined because there are a billion implementations, or how it's integer hierarchy, so how much precision the integers hold and what those types actually mean in practice, is, quote, completely failed. Now, completely failed is maybe not something I would use to describe the most used programming language in the world, but they make a good point, especially if you read through the links. There's a great deal about programming ABIs, so the way different languages talk to each other, which is primarily by talking to C and then having a way to read things from C. So this is quite good. It's a long read, and it's quite opinionated. Something that's a bit shorter is C strings and my slow descent into madness. I mentioned when we were discussing character arrays yesterday, or C strings, that there are no C strings, they're just character arrays. This is a very good read about the inconsistencies and difficulties of working with strings in C. A lot of these C programs are actually quite short and legible. What's important to keep in mind is that everything that you basically do with strings in C is unsafe. They go through some attempts to make C safe, especially for string processing, but C is generally unsafe, and I mean this in the memory unsafe sense. You are typically manipulating things with pointers directly in memory. There are almost no safeguards. With a modern compiler, you can add warnings that'll tell you that you're doing something unusual. But generally, what you do in C is unsafe because that's sometimes the most performant way to do it. Not always. With strings, with character arrays in C generally, this is quite dangerous. In fact, doing even basic operations with strings in C can be confusing and not well defined. There have been attempts over the years to make C safer or more reliable. C++, which you'll learn a bit about, I think next week, is much safer than old-style classic C, which is what we've been doing so far. It's still not memory safe. I think this year, C++ 26, there is some move towards making C++ generally memory safe, but I don't think it's entirely done, and it's certainly behind the memory safety of other programming languages that you may know of. For example, Rust, which is generally considered a memory safe language, though it has some other issues, especially around the performance of memory allocations and things like that. This is something you should be aware of, and if you're interested in programming language design generally, these are really fun reads because it tells you a lot of things not to do and can help you assess how well a new programming language that you want to learn is actually going to serve your interests. C is always good to know because it is a very small language. It's not really suited for everything. A lot of things are still written in C, like device drivers, and that should probably scare you a bit, because if you make a memory safety issue with a device driver, suddenly your whole machine is broken. But C is very good at certain things. It's very good at working with large arrays, doing numerical calculations, because everything's simple enough to be predictable. I wouldn't use it for strings. I wouldn't use it for system-critical things where you need your machine to not break suddenly. But it's good to keep in mind. That's all I wanted to say about some of the horrors of C. There are things that are worth knowing about this, and there are things that are sort of trivia.